to welcome Iain on this first session after the keynote talk of Gaël. So Iain will speak about physics-informed GP models, priors.
Okay, so thanks very much for the introduction. And thanks to the organizers for inviting me to this wonderful venue. It's my first time in Cambridge, so I'm a bit dazzled by how amazing everything is. Right, so my name's Iain Henderson. Oops, yeah. I'm currently a lecturer in applied maths at ISAE-Supaéro in Toulouse. And today I will talk about physics-informed Gaussian process priors. So here's the plan. We'll go through this further during the presentation. The things I'm going to talk about they're getting a bit old because the last paper was published in 2024, and they all concern my PhD work with my two advisors in Toulouse. So one of them is Olivier Rostand, whom you might know, who's from the machine learning and uncertainty quantification community, and Pascal Noble, who comes from fluid mechanics and PDEs. So I think you'll get a gist of both worlds in my presentation, hopefully. And was pursued at INSA Toulouse in France. Okay, so what's today's topic? So the question will be the design of Gaussian process priors, okay, Gaussian process models for solving problems that are related in some way or another to PD. So PD means partial differential equations, which are the typical equations you encounter when modeling physics. And what I will do is focus on the mathematical aspects, because when you study PDEs when you're a student, you learn that there's a bunch of very particular ways to tackle them, to understand them, to formulate them, and they're not really standard in the GP community, because, for example, in GP models, you can assume that your kernel is continuous, for example. And sometimes this is something you don't really want to do when dealing with PDEs. Okay. So the first thing is try to comply with what I'm going to call the distributional formulation of a PDE, which is very close to the weak formulation, which actually has a lot of impact in practice. Okay. For example, if you use a finite element solver, this is the thing you're trying to solve. Okay. And I'm going to also talk about particular function spaces, which are very important in a PDE theory. So I'll take these notions and I'll try to fit them in a GP model. And if I have time, I think I won't, but I'll try to describe some practical applications. Okay, so in general, how do we design a GP? Okay, so first of all, yeah, I'll just go through what's a Gaussian process, because I don't think it will. Perhaps some people, it may be a bit old for some people in the room. So, what's a stochastic process? Well, it's basically a family of random variables indexed by some set. Okay, and so it's basically a random function. And among all the random function models, one of them is very important. It's the class of Gaussian processes. So they're the random functions such that for any finite subvector, you're going to end up with some multivariate Gaussian distribution. And in practice, how do you manipulate this kind of object? Well, two things. You're going to have to look at the mean function, okay, just the expectation of your random variable, and then you'll have the covariance function, which is the covariance between u of x and u of x prime. And I'll denote it with this notation. I won't talk about the mean function, I'll assume that it's 0. But the function k is a positive semi-definite, symmetric. And this property is equivalent to being the covariance function of some Gaussian process. So actually, in the talk, we'll be focusing on how do we choose k. That will be the whole game. How do I choose this kernel function? Okay. So, very famous example of a Gaussian process. So this is just a picture of a different realization. So what are the typical random functions you can generate with a certain Gaussian process called the Brownian motion, right? So the kernel is going to be given by this formula, and you end up with these very squiggly functions, which people use to model, for example, some stuff in finance, which I don't really know about. Okay. Right, so in practice, how do we use Gaussian processes to approximate functions? Well, so let's say there's some function that I don't know, but I want to approximate it, and I've got a set of pointwise values. Since I don't know it, and let's say I have a Bayesian approach in life, so I'm going to assume that this is actually a sample from a Gaussian process. So in other words, I'm going to put a GP prior over this function. Okay, now that I have my prior distribution and I have my data, what I'm going to do is just condition my distribution on the data. So I'll end up with a second Gaussian process distribution, which has a new mean function and a new covariance function. And now that I have this, so this will be exactly a conditional expectation, and this will be a conditional variance. How do I do estimation with this? Well, at some new location z, I'll approximate u of z by simply the posterior expectation at this place. And I have a related uncertainty, which is just the variance at this point. And all of these formulas are explicit. You can compute them using basic linear algebra, so that's very nice. So how does this look in practice? So you have some function, okay, which may have which is a whole bunch of properties, but you only have a small set of pointwise values. That's all you know. And if I do this procedure that I've described, we typically end up with something like this. So in black, there's the same function that I'm trying to approximate. The posterior mean is going to be the blue function. That will be my approximation function. And then I'll have the uncertainty, which will be plus or minus 2 times the posterior standard deviation. And then I drew some conditioned samples here with a dashed line. Okay. So that's just I haven't actually made any choices on the kernel yet. But the thing is, suppose that you know that your function is smooth to a certain point. Well, this is actually something you can take into account when you choose k. So what's the theorem? Well, if your kernel is of class Cn, plus some technical condition, then your prior distribution, so the prior information you're going to give to your Gaussian process model, is gonna only focus on your target regularity. Okay? So if you know that your function verifies this, then you're going to want to choose a kernel that verifies this property. So that's one type of prior Gaussian process prior design. And another type is the following. So let's say that you know that your target function has some invariance, some linear invariance. It's periodic, or it's translation invariance, or whatever. So you're going to want to only look at potential solutions that also verify this invariance. And how do you do that? The typical way is to choose a kernel that verifies this constraint. Whatever z the input, then you can ask that your basis functions verify this. Also verify your invariance. Okay. So here's a very wrong proof, but just to get the idea of what's happening. What's the link between this and that? Well, if you look at the covariance of your target, your target, you're going to look at LU of z, and what you know is that the covariance is bilinear. So this is a linear operator, so both of them can just come out of the expectation, and you end up with something like this. And what you see is that this thing is going to be 0 because you've assumed that you have this property. And now if you take z is equal to z prime, you'll get that the variance of LU of z is going to be 0. So you end up with a random variable which has a 0 variance, so it has to be constant almost surely. And this is typically how you impose this kind of stuff. Okay, so two types of prior information that you're going to want to impose in your GP model. Okay, so that's an example. If you have a periodic kernel, then you're going to end up with a prior Gaussian process prior with periodic samples as well. Okay, so now I'm going to work on this linear invariant stuff, but my linear constraint is going to be a partial differential equation. Right, okay. So yeah, that's just the takeaway message. We know that if you choose the kernel well, then you can take into account prior information. Okay. And the whole point of this is that it helps you restrain the function space that you're trying to work in. Okay. So just to formulate the problem in a better way, you've got some function that you're interested in, you only have pointwise values, and you know that it's the solution to some PDE, where this L is going to be a linear partial differential operator. Then you're going to want to try to impose in your GP model this prior information, okay? And also, because PDEs, they also come with function spaces, I'm going to try to impose a correct energy space, which in my case is going to be a Sobolev space. Right. So just a nice example where the world is nice and you can write down everything and you don't have any smoothness problems. I'll focus on the heat equation. Okay, let's look at the heat equation. So you have some differential operator which has space and time, and you have some initial data, and you're interested in estimating the whole solution, and what you have are only pointwise measurements. So you can imagine sensors on a rod, okay? And you know two things, you know your measurements, and you also know the underlying dynamics, right? And so we've seen that you're going to try to look for some kernel. So since you're modeling a space-time function, your kernel is going to have space and time inputs. You're looking for a kernel that verifies the constraint that we've identified earlier on. Okay, and what happens if you do that? So again, here's the real solution with the measurements. So if I do Gaussian process regression, but with some general kernel where I don't tell the model anything about the underlying dynamics, you end up with something like this. And in particular, the uncertainty is very bad because, of course, it doesn't know that actually you're looking at a diffusion problem. Whereas if you use a correct kernel, you can end up with something like this. So I don't know if you're able to see, but you also have 3 layers. But the 2 uncertainty ones are very small because since you've told your model that you're looking at a diffusion problem, then it knows that you're going to have something like this. Just to look at the expression, I'm not really going to delve into the details. There's a general way of building such covariance functions, but you have something very explicit in this very simple case, okay, where you have something which is stationary in space, but actually it's not stationary in time. Okay, and actually you want that because you see that you have a specific, I mean it's not time invariant, right? If time goes on, then it goes flat. And actually verifies our constraint. Okay, so I mean we have a nice example, okay, where we know, I mean obviously we can do some really nice things. Now let's look at a not so nice example. Let's look at the transport equation. Okay, so very simple. Derivative in time is equal to derivative in space times a speed parameter, and you have some initial data. And it's not too difficult to see that the solution is just going to be translation of the initial data, right? You can imagine just the initial data being translated in space. Okay, but now, if I'm a bit, if I look at the details, what happens if my initial data is not smooth, right? So you cannot differentiate this thing. But the thing is, how can I check that this is a solution of my PDE if I can't even differentiate it? So what's the problem of this? But the thing is, you really want this to be the solution, right? Because this is actually the only one that makes sense from a physical point of view. And the way that people deal with this kind of problem in PD theory is that they're going to go back to the physics, because this actually reflects a Balanced law, right? And typical Balanced laws, they come from macroscopic energy balance, for example. Okay. So how do you do that? So this is exactly what we're going to be doing. Okay. So now instead of saying that my PD is going to be valid pointwise, okay, I'm going to require that all the smooth and local averages of the PDE are going to be 0. Okay. So I take my PDE. So if the world is nice, this should be 0, but we've seen that in my particular case, this may not be 0. What I'm going to do is multiply this by a test function, a very nice smooth with compact support this function and integrate over the space-time domain. And what I'm going to do is transfer, using integration by parts, I'm going to transfer the derivatives on the test function. And what you see is that I don't have any regularity problems anymore on my target solution. Okay? And this is exactly what I'm going to call the distributional formulation of my PDE. Okay? I mean, this is some sort of duality stuff, actually. And this is how people deal with non-smooth solutions in practice. Also, non-smooth solutions, they do happen in real life. For example, the sonic boom is exactly a discontinuity in your solution. Okay, so first thing, distributional formulation, and then if I have some target energy space, I'm going to have to also deal with this. I'll do that in a second time. Okay, so okay, my question will be the following, and I'll have, I'm sorry, this is maybe, it's quite heavy notationally wise, but I'm sorry about that. So I have a random field model, okay, and the question is, how do I impose this constraint, okay, that we've identified, but I'm going to try to impose it in this distributional sense, as I've told you, right, with test functions and all that, integration by parts. And actually, there's a theorem. So there's a bunch of assumptions which I'm not going to describe, but basically what happens is that what we've seen formerly, you know, there was an equivalence between these 2 points beforehand, where L was some linear operator. So if L, in this particular case, if L is a differential operator, then this thing that we had identified also holds if I put distributional sense everywhere. Okay. So what does that mean in practice? It means that this tells me that I can deal with well-suited PD priors, but I don't have to worry anymore about this discontinuity stuff, which is actually, I mean, from Gaussian process point of view, it's not standard at all, right? And you can see here that there's no continuity assumption on the solution. It may be as discontinuous as this indicator function, for example, right? So that's the whole point of this theorem. Because I have this distributional solution, I can also take into account non-smooth solutions. And also, actually, I don't have to assume that anything is Gaussian in this theorem. Okay. So that's nice. Okay, that's an equivalence. But the thing is, okay, I know that I have to choose my kernel like this, but this doesn't tell me actually how do I find such a kernel. So I'll just provide you with some simple examples. So let's go back to this heat equation stuff. So actually, there's a very general representation formula, which goes as follows. So basically, it's just convolutions, okay? Convolutions of some kernel with a function which is called the heat kernel. And if I take a specific K0 here, I'm going to end up exactly with the formula that I had given you earlier on, okay? So perhaps don't really focus on the formula, but just remember that there's a general form for this, for the heat equation. And now if I go back to my mean example, okay, like the bad one, the ill-behaved one, actually there's a very close, very similar formula where I actually end up with exactly the target form that we knew was the correct one. Right. And so they both verify the constraint in the distributional sense. Okay. And a nice thing also is that they also depend on the physical parameter. Here I have a diffusion coefficient, which appears in KT, right, or in here. And so they appear as hyperparameters, meaning that I can estimate them. Okay. So what is it? Okay. Right. Okay. And actually, if you look at the literature, there's a whole bunch of people who found kernels that verify this, that they didn't bother about this distributional stuff. And the main message is that, okay, you can just use them and don't really worry about pointwise problems if you use this distributional formulation. Okay. Right, I'll go for 5 minutes. So I've done this thing. I'll briefly talk about this. It's a bit technical, but perhaps I'll just talk about the message, and then I'll show you some pictures, and we'll be done. Okay, so I've talked about this weakened formulation, but there's another notion which is very important, which is that of energy functionals, if you look at PD theory. So let's go back to this heat equation. If you take a solution of this, actually, you have this sort of energy balance. If you look at the L2 norm, actually it's not an energy, but anyway. And you can see that here you have a spatial derivative that appears, and you have to take its L2 norm. Okay? And this tells you that you have a diffusion phenomenon. Okay? And now if I take the wave equation, this time I can look at the energy at time t, so kinetic energy, okay, so speed is squared, and then potential energy, which is written like this, and you also have the gradient, the spatial gradient appearing, and actually these quantities are conserved. So what's the message of this? Well, the message is that if you have a PDE, sometimes you have some norms which are very naturally associated to them. And they often make use of the L2 norm of the solution as well as its derivatives. And that's the new point, and that's the whole point of Sobolev spaces. Okay. So what's the idea between Sobolev spaces? So let's look at this nice hat function. So if you're a first-year student, you learn that this is not differentiable here, okay? And then it's catastrophic and you can't do anything, okay? But the thing is, this thing on the right-hand side actually has a finite energy. So it's regular, but in the energy sense. Not in pointwise sense, but in the energy sense. Yeah. So there's a way called the weak derivative with which you can say that this thing on the right-hand side is exactly the derivative, so in the weak sense, the derivative of this thing. Right? And that's the whole point of Sobolev spaces. Sobolev spaces is, so this H1 is going to be the functions with finite energy, okay, such that their derivative exists and also has a finite energy. Okay. And one problem with the theory is that it's not because you're looking at a Sobolev space that you have continuous functions. And in Gaussian process modeling, you're super used to assuming that everything is at least continuous. And sometimes, if your target space is H1, then you don't want to make this assumption. Okay. Right. So we have this energy space, which can be generalized to several dimensions. And you don't want to make any continuity assumptions. So that will be my question. Under what condition can we ensure that our Gaussian process model verifies this, okay? So the solution is going to lie in the correct target space. Okay. Before tackling this, perhaps it's good to look at looking at L2, right? So just forget about the derivative and look at the conditions under which you can ensure this thing. And actually, you have a very nice necessary and sufficient condition, okay, which is easy to formulate. And it goes as follows. Your samples are going to have a finite L2 norm if and only if this integral is going to be 0. Okay. So this way is very easy because if this expectation is 0, then obviously this thing is going to be, you're going to have a finite L2 norm almost everywhere. But the other way around is a consequence of a very, very strong theorem called Fernic's theorem, okay, which is only valid for Gaussian processes, Gaussian measures. Okay, so basically what you're going to want is to have this finite integral, finite L2 integral. And what's nice is that this, if you're familiar with spectral theory, there's a bunch of different ways to understand this condition. Right, so one way to interpret this is to look at the integral operator associated to the kernel. Yeah, I know, 2 minutes and then I'll be done. And I'll just skip the last part. If you look at this thing, then your kernel, this provides you the Mercer decomposition of your kernel, basically. And this thing, okay, so you're going to have eigenvalues. And if you take a look at this expression, now that you have your Mercer decomposition, you're going to end up with a series of the eigenvalues. So you're going to end up with a trace class operator, that's cool. And there's an RKHS interpretation, but I won't delve into this. So for the theorem, now if I replace L2 with HM, then actually I exactly have the same criteria, but I have to add some derivatives. Okay. And also you have something similar with the trace and the Mercer type decompositions. Right. Okay. So I mean, perhaps just a comment. no continuity assumptions there. Okay, so this is an if and only if. Whereas if you want to find if and only if conditions for the continuity of a Gaussian process, it's actually super hard. Right? So this is remarkable that this is easy in some way. Anyway, so that's a bunch of characterizations. You can also do work with LP Sobolev spaces. That's just for fun if you like weird math, but you can also do that with also if and only if conditions. Perhaps I'll just skip the comments and show you some images. Right. So an application that we've targeted is the 3D wave equation. Okay. So you have this differential operator, and you'll be interested in finding kernels that verify your PD constraint, as we've identified. And for this, you're going to use representation formulas. Okay. So this is called the Kirchhoff formula, where you have where you can involve your initial data with some measures. Okay. So these are spherical averages. And you're going to end up with a complicated formula, but actually it's very similar to what we've seen earlier on with the heat kernel and the transport equation. Right? Okay. So you end up with this, and actually, if you use a kernel like this, you can tackle some problems such as approximating the initial data of your wave equation, which is actually a problem that people are trying to solve in real life. This is called photoacoustic tomography. And now just for the image. Okay, so you have a numerical simulation with some initial data, which is shaped like this. You have some sensors. So you have some data associated to each sensor, and then you do Gaussian process regression, and then you approximate the initial data. And the typical thing you can obtain is this. On the left, you have the correct initial data, and on the right-hand side, you have the GP approximation. Okay. So that's quite nice. So this will be the end of my talk. We will have an open PhD position for next year, so I'm just seeing this in the world if it lands in someone's ears. Thanks you for your attention.
Hello. Yeah, so go ahead. Yeah.
I'm curious about the domain over which you define the Green's functions of the differential operators. So in general, we want to work with compact domains.
Yeah.
So we kind of do the sleight of hand and say, let's work with the whole space and see if they approximate. Like, can you comment on that?
Yeah. Okay. So all my formulas actually, so they all rely heavily on Green's functions, as you said, and that's actually one problem. Yeah, so that's one problem. So perhaps the thing is, everything is not lost because, let's go back to the theorem. Right, so the theorem doesn't make any, yeah, this only has to be an open set. So this holds, okay, right, on any domain, especially compact, for example. Okay, but the thing is, your Green's function is going to have two inputs, right? And then formally you can write things like this, but it's not going to be a convolution anymore. It's going to be super heavily computationally expensive, but you can write it down. So that's one thing. One thing that actually, with a colleague, we're trying to do a data assimilation in 1D, and actually in 1D what we're trying to do, one way you can escape this, it's easy to do in 1D in multiple dimensions. I think it would be much more difficult. So this would be your domain. You can impose, you can first say, okay, if I forget about this, I mean, point-wise, I mean, my PD is going to hold in the interior of the domain. And then afterwards, for example, if you have Dirichlet boundary conditions, you can condition your kernel so that you have Dirichlet boundary conditions. Yes. Right. But now if you have complex boundaries in multiple dimensions, I don't really know how to deal with that. Okay. Or perhaps cut it in subdomains and then do a linear approximation.
Here's another question here. So regarding moving to this, moving to Sobolev spaces.
Yes.
What's the real benefit to this? Because Sobolev spaces are just dense within L2, so you've kind of already got all of your Sobolev solutions already just by solving it in L2.
Yeah. So the idea is just that I've written it somewhere actually. Yeah. Is this? Oops. You want this to be as small as possible, right?
Okay.
Because you're going to want to, I mean, yeah, it's basically a form of dimension reduction, basically, right? That's just the idea that I have behind it. I mean, the way I understand it.
Is there any online question for Iain?
Not a question, but a quick comment
Yeah.
about the GP on the boundary conditions. So there is a paper which combines Gaussian processes on your boundaries and then use a piano in the interior. So there is a way to overlap.
Okay. Oh, I mean, are you referring to the Lange Hegerman paper? Because there's one where actually, yeah, I mean, now that you mention it, you can, there's this paper in Eurips, I think, where you can impose your boundary conditions if you have algebraic curves as your boundary, for example. You have algorithmic ways to deal with this.
And Dirichlet boundary conditions. So normally will be hard with the Dirichlet boundary.
I would have one more question. So
No, we have to move on. Thank you very much.
Yeah.